We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
3, 2, 1. We have a liftoff. 32 minutes past the hour.
Senior engineering students are working directly with NASA. 6 students were selected to participate in the highly competitive Exploration Systems and Habitation 2018 Academic Innovation Challenge.
Our industry partner is NASA's Advanced Exploration Systems, and specifically we're working on the Resource Prospector mission.
Resource Prospector is a robotic rover that NASA is sending to the poles of the moon to mine for resources like water.
In 2009, NASA proved with the LCROSS and LRO missions that there are potentially resources that we could use on the moon. So where they stand now is trying to find a way to get there, mine those resources, and set them up in a way so that they can be utilized to help propel us further into the solar system. This is a critical piece for NASA as it's really expensive to launch any amount of mass off and out of Earth's gravity well.
Our project is actually a very small portion of the overall design and engineering work going into this mission, and we're specifically focusing on testing the wheels themselves. In previous missions to the moon and to Mars, NASA has sent the rovers to large flat areas, but the poles have several smaller craters that they're concerned with wheel performance in.
Given the traction concerns on the moon, we want to make absolutely sure that our rover will have the traction necessary to propel itself across the moon's landscape. So what our project aims to do is to create a way of testing the wheel-soil interaction in the reduced gravity that the rover will experience when on the moon. Currently, there's no system that NASA has that can test wheel-soil interaction at this reduced gravity. So our project creates a small-scale test bed that can go into a parabolic flight aircraft, which will simulate the 16G to enable that wheel-soil interaction testing in an environment that simulates the moon's gravity.
Parabolic flights have been used to model reduced gravity scenarios since about the 50s. During a lunar gravity flight, there are between 40 to 60 parabolic arcs, and during each one of those arcs, there's about 30 seconds where the plane experiences true lunar gravity. Those 30 seconds are about the only window we have to test this wheel-soil interaction. And the issue that comes with that is during the arcs, the system will also experience 1.8 G and has to be able to maintain itself during that.
So the theory behind single wheel testers is you have 2 relative velocities, the angular velocity of the wheel and the linear velocity, which would come from the rover in reality. If you can control the difference between these 2 velocities, you can get a lot of good information about how the wheel will behave in real life. Our tester collects 3 pieces of information: slippage, which is the difference in these 2 velocities, sinkage, which is the vertical displacement of the wheel, and drawbar pull, which is a force on the wheel.
Our design is a rotating annular trench bed. We've had this idea basically from the get-go. Really cool to see this design start from a sketch and go all the way to a physical design that we can control.
Most single wheel test beds run linearly. We decided ours was going to be a circular test bed. This allowed us to reduce the size and weight of our test bed.
Another big decision we had was where the linear velocity should come from in the build. Physically, moving the road under the wheel and moving the wheel over the road are identical kinematically. In the end, we chose to move our road under the wheel because it lets us reset the regolith continuously.
In the course of this project, we were actually given the opportunity to travel out to both NASA Glenn and NASA Ames Research Center and got to see how real engineers out in the field perform some of the tests that we've been performing on this design ourselves. And that was a fantastic opportunity and was very helpful in the overall design process.
With the help of our design, NASA will be able to complete the R&D phase of the Resource Prospector mission, and hopefully if the mission is approved, they'll meet their launch date of 2022 to 2025.
What we've learned and what we've experienced through this process is really valuable and applicable to anything we do with our careers. It's really been a unique experience for us.
We'd like to extend a sincere thank you to our client, Paul Banasiewicz, as well as our mentors, Drs. Hitt and McDevitt.
My name is Darren Hitt. I'm a professor of mechanical engineering. I am the faculty mentor for this project.
I'm Ryan McDevitt. I'm the CEO of Benchmark Space Systems in South Burlington, Vermont, and I'm the industrial mentor for this project.
My name is Paul Benicevic, and I'm the rover mission systems engineer on the Resource Prospector mission, and also the mentor of the University of Vermont XHAB team. Resource Prospector is a mission to send a rover to the polar regions of the moon to search for water. You can't do that without a solid understanding of how the rover interacts with the lunar regolith in the appropriate lunar gravity environment. So a big shout out and thank you to the University of Vermont team for helping us better understand that environment. We couldn't have done it without you. Best of luck and thank you very much.
Vermont.